Let's just wait for a minute until others join and then we can start the session. Can you please confirm if I'm audible in the chat? Uh, Good evening, everyone, and welcome to Week 10 live session for the course Deep Learning for Computer Vision, conducted by Professor Vineet and Balasubramanian. So, my name is Aveen Dayal. I'll be the TA for this live session, and we're almost towards the end of this particular course. I think week 12 is the last week. We'll also be having an extra session. I think the details for that will be shared soon. So, up till now, we've covered a lot of different concepts in computer vision. We started off with the very basic element in computer vision, that is nothing but what is an image, how do we represent an image, like with matrix format or functional format. Then we talked about several different filters which can do several different detections, like edge detectors, blob detectors. Then we also had more sophisticated traditional algorithms like SIFT algorithm, which basically tries to identify what are the key features that are present in an image, and based on that you can try to do a lot of different applications like image stitching or object detection, etc. Then we moved into the deep learning aspects of computer learning or computer vision, where the first we try to understand what are neural networks itself. So we started off with a very basic neural network, which is the perceptron. Then we moved on towards the modern day neural networks, which is nothing but the multi-layer perceptrons or feed-forward networks. These are the same names for it, and also deep learning. It's the same thing. And we understood a lot of different concepts in training these networks, like what should be the loss function, what should be the gradient update rule, the back propagation, and how do we speed up or make the learning process efficient, like techniques like regularization, dropout, normalization. All of these things we've seen. We also saw variants of gradient descent, like a batch gradient descent, mini batch gradient descent, stochastic gradient descent, also different optimizers like RMS prop optimizer, momentum optimizer, Adam optimizer, etc. Then we moved into the actual neural network algorithms which are relevant for vision applications, which is convolution neural networks. And convolution neural networks are fundamentally built on the operation of convolution, which is the same traditional convolution operation, similar to the traditional convolution operation, where you have a filter that filters lights on the image, and each patch of the image that the filter sees, it tries to extract some relevant information. And what is that relevant information? That is basically defined by the way the filter itself is constructed. So if the filter is like an edge detector filter, then at each patch in the image, it will try to extract the edges. If it is like a blob detecting filter, then at each patch of the image, it will extract the blobs. But in neural networks, convolution neural networks, what we say is let the user not define what these filters are. Let the algorithm learn itself. So we have these thousands of filters which are randomly initialized, and throughout the training process, we make sure that the algorithm itself learns at each stage what should be the right filter so that the most relevant information is extracted from that particular input. And that is the basic idea. And there are also some other idea for what do you say, motivation factors like spatial invariance and location spatial invariance, and then also parametric computational efficiency using CNNs. All of these also led the way to these algorithms. And then we talked about slightly complicated tasks other than just image classification, like we talked about object detection, semantic segmentation, instance segmentation, etc. And we saw algorithms relevant to all of these tasks. Then finally, we went to sequence models, which, while they have not been actually defined for image algorithm, image input data, people have used them for images, especially in tasks like visual question answering, image captioning. People have used these sequence to sequence models like RNNs, LSTMs, all of them, in trying to solve these particular tasks. So, uh, just yeah. And after that, we've talked about transformers architecture. Transformers architectures are very effective in identifying what is the correlation between the input sequence data itself. Like, for example, if the input is a bunch of words, what is the correlation or the relationship between each word present in the input data? And while transformers were traditionally built for sequence to sequence data like text, uh, but eventually we saw vision based transformers where people try to first split the entire image into patches. So, this is what we discussed last session, where we had this original image, we split it into something called as patches. This is a patch, and then now each patch is treated as a, you can think of it like a token. And the goal of it, this tokens, all of these tokens are sent to VIT. This is nothing but the vision transformers. And the object of this is learn learn the relationship between, or correlations, whatever you want to call it, between all the tokens or patches. And based on this correlation, you can basically try to solve different tasks. You can do your image classification, detection, segmentation, all of these. So while Transformers traditionally works on tokens, and it kind of takes away the idea of CNNs where we had the spatial invariance and all, but it still works a lot better with the help of using a lot of data. So with the help of a lot of data, it tries to learn a lot of important features and everything. And like more sophisticated algorithm like Swin transformer, which uses the shifted window concepts and all, they still bring in the idea of these convolution networks, global relation thing. So then in today's session, we move on to another another set of algorithms, which are the generative algorithms. So generative algorithms, I think all of you are familiar today with the works of ChatGPT, Gemini, and then Claude and Cursor. All of these fall under the family of generative algorithms. So what are these generative algorithms? Let's maybe first discuss that and then move on to the questions. So typically there are two types of algorithms. One are discriminative algorithms, just call it as disk. The other are generative algorithm. Okay. So what does a discriminative algorithm does? Like the name suggests, it tries to discriminate the input among the different classes that are present in the task. Like for example, simple image classification task. Let's say I have 10 classes. So in discriminative algorithm, the goal is, given the input image X, I need to place this into one of, not just one or multiple, like into some classes from input to a fixed set of classes. So here, in a way, we are trying to discriminate between the different classes for that particular input. If you think about it in the space, in the embedding space, let's say I have two classes, very simple, blue class, then there is green class. So discriminative algorithms will try to create these classifier, will try to create this classifier which will discriminate between the two classes. And based on the test input example, let's say the red point is here, it will try to identify what is that class based on this classifier. Now, generative algorithms don't have to discriminate between the classes. What it does is it tries to understand what are the fundamental distributions, underlying distributions of each of these different classes. So in discriminative, you don't need to understand what is the underlying distribution of these blue class. So what is the underlying distribution of blue class? What is the underlying distribution of green class? You don't understand. You just try to, given an input, you try to figure out whether it's in blue class or green class without even really figuring out what is the actual distribution of blue and green class. Generative does the opposite. Generative is like, let's first try to understand what is the underlying distribution of each of these classes. Then you can maybe use these for different tasks. You can either generate a new sample from these underlying distributions for that particular class, or you can also maybe use that information to do discrimination, etc. So typically, how does it look like in the embedding space? The same example, blues are here, green is here. In generative algorithms, we try to understand what is the fundamental relation, sorry, what is the underlying distribution of blue, what is the underlying distribution of green. Now, how will the inference time it looks like if someone asks, okay, generate a sample which is similar to green. So then ideally the generative algorithm will generate a sample from this distribution. It will sample this particular point and give that as an output. So I hope you're able to differentiate between generative algorithms and discriminative algorithms. If there is any doubt, as usual, please unmute and you can ask, or you can also post it in the chat. So even the LLMs today, what we see, right? The VLMs, LLMs, all of them form under generative algorithms. Why? What does LLM do? The simplest chat GPT, if you take, forget about images and all the chat, just text based chat GPT. Okay. What does it, how is it even built? It is built on a lot of internet data. And what is that internet data? What are we trying to model in that training of on the internet data? We're trying to learn the fundamental relationship between how a sentence, paragraph, or natural language is usually formed. So it goes through all that internet data. It'll try to understand, okay, if the word the is used, it's an article. Typically, what follows the word the. And similarly, to understand, okay, a sentence, if it's given, what are these, adverbs, what is the preposition, sorry, what are the different parts of speech of this particular sentence, all these relationships will try to learn. So it is like trying to build the underlying distribution, that is the relationship in which how these sentences are formed, right? That is the underlying distribution. It will try to learn that. So that is why it is called as language modeling, where it tries to understand the underlying distribution of how languages are created. So that is nothing but exactly what generative algorithms objective is. Try to understand the underlying distribution of the classes rather than just discriminating the two classes. But we can also solve a lot of discriminative problems even after learning the generative algorithms, just like how ChatGPT does. Well, initially you train it in a generative fashion, you can also solve a lot of discriminative tasks too, using that information or knowledge what it has learned. Okay. So in this session, I think in the recorded lectures, Professor touches upon the most popular ones, the most popular ones, which is the variation autoencoders and generative adversarial networks. Of course, these were very popular probably like 6 7 years ago. Now the direction in which it is moving, it's all diffusion models and language models. But yeah, nevertheless, these are also still relevant in many of the tasks which are still helpful and can be solved using these algorithms. So as usual, we have two parts in this session. First one, I'll discuss questions, and then we can discuss the code walkthrough for this particular session. Okay. The first question is based on variational autoencoders. Very simple. So we know that variation autoencoders computes the evidence lower bound. And the question is, why do we have to even compute the evidence lower bound? And why can't we just directly maximize the likelihood? So what is the reason why we're going to evidence lower bound? Pick one of the correct options. So some terminologies, xi is the input, z is the latent variable, P of xi given z is the conditional distribution of x given z. Similarly, P of z given x is the posterior of z given x. So based on these thing, why do we have to go for evidence lower bound and not why not maximize directly the likelihood? Quickly pause for a few seconds. You can try to read the question and options carefully and answer this particular. That's true. Correct answer is both one and true. No, one and two are true. Let me explain. Let me first explain what variational autoencoders are, and then we can go back to the question and solve. Okay. So this is typically how a VAE architecture looks like. So the input images is X. Then you have two components in your VAE. One is the encoder component, and the other is the decoder component. On a very high level view, what does the encoder does? It tries to encode all the information of the input and project it into a lower dimension, into a hidden dimension space or embedding space. And the decoder will basically take this hidden dimension space vector, that is Z, and tries to recreate the input. So this is also very similar to what autoencoders are. So you can always look into these family of algorithms called autoencoders. Variation autoencoders is a special type of autoencoders, as the name suggests. Now, what is the difference between autoencoders and variation autoencoders? Is in the variation autoencoders, we try to map the encoding output to a distribution rather than a fixed vector. So in autoencoders, maybe let me give you a high level overview. You have an encoder, you have a fixed embedding vector, which we call Z. Then we have a decoder. Obviously, the input will be X to X. Now, this fixed vector Z is the problem because what is the most you can do? You can map this X to a fixed point, and you can always get at the most the X which you already has an input has as an input. You can't really get a variation to that particular X. Like probably the user is not interested in generating X itself. The user is interested in generating a slight variation to X. Let's maybe call it X tilde. But with this particular way of learning, we're making sure that the embedding will learn like a pointwise representation. X mapped to fixed Z. Now fixed Z goes back to X. It can never generate a slight variation to the input because it's not learned that. No, how can we come up? Possible? How do we avoid this? Let's not keep the Z fixed. Let's not. This is fixed over here. But in the actual VA, they said, okay, let's not keep Z fixed. Instead, let's learn a distribution for Z. Now, that is where these terms come into play. That is where mu, sigma, and epsilon come into play. So what the algorithm says is map the encoding output to one point in a distribution. You learn a distribution, and then the Z is sampled from that distribution, and the decoder will generate a slightly different variant of that input. So that is what this is now basically doing. So how do we model this mu sigma? So typically people say, let's model as a Gaussian distribution with mu and sigma value. And now the Z is nothing but the sample. I'm just writing sample as like this. Z is coming from a sample of this normal distribution. So encoder goes to normal. we learn from the encoder, we learn the mu and sigma values, and then we have this normal distribution. And once we have this normal distribution, you sample z from there, and then you generate the output from this z. So in this way, you're able to even generate points which the model has not seen previously, like input which model previously has not seen, a slight variance of those. Okay. Now, there are two types of losses in variational autoencoders. The first is the reconstruction loss, which is written on the top. The motivation for this loss is very simple. Tries to basically make sure that the reconstruction which is happening, it is as close as possible to the input which you have. That is the idea behind this reconstruction algorithm. So you can, the most simplest way to think about is pixel to pixel mean squared error. So if you want to generate the same x as an output, you want each pixel to look the same way as the output pixel to look the same way as the input. So you just calculate the mean squared error pixel to pixel. That is the reconstruction. But we also balance it with a second loss called KL divergence loss. Now, this KL divergence makes sure that this distribution which you're learning, right, this mu sigma, it is as close as possible to a normal distribution P of Z. Why? Because it can very likely happen that if you don't have the scale divergence, it will just quickly fall back into that fixed Z, because there's no regularization, there is no constraints, right? So it will quickly fall back to that fixed Z, and you'll only generate that particular point-wise representation. So to make sure that doesn't happen, you enforce that okay, whatever distribution you're learning, it is as close as possible to a standard normal distribution. So this particular block inside will not be a fixed representation, it will be a distribution that is being learned. Now, that is how the KL divergence loss comes in. Now, how did it actually come up like this? So, the heart of it, bottom equation which you see, right? That is what we, this is the likelihood. That is, what is the log likelihood? It means given these input samples, what is the distribution that will fit this input samples? That is what we're trying to learn. That is what this distribution is also trying to do, right? Given an input x, what is the distribution that is likely forming these samples of x? And we take the log likelihood. Now, if you expand that inner formula of this marginal p theta of xi, this is what it looks like. Because we have a hidden variable z, it will look like a joint distribution between the input and the latent variable z. Now, this joint distribution consists of two terms. Uh, it typically, when you start optimizing it, posterior comes out over here. The posterior is used in this, which is nothing but P of Z given Xi. Now, this is very hard to, uh, because we don't know what this is, right? Sorry, this is not the posterior. Sorry, that's also, this is not easily trackable, because we don't know what this distribution is, and it's hard to compute this distribution. So this is the reason why we can't directly optimize this particular loss function. Instead, we approximate this with the help of another another network q5, and then with the help of that q5 we are able to uh, with the help of this q5 we are able to approximate this particular objective function, and that is where the elbow loss comes into picture. So this is one of the reasons why we can't directly maximize the log likelihood. Instead, we'll have to approximate it with q, and then with that q, we can then calculate the elbow loss, and that you optimize. So these are the 2 points. Data distribution, this is unknown anyways, so it's kind of debatable. Some people say that this is also a factor for why we don't use maximum likelihood directly. But some people say this is not a direct contributing factor, but an indirect contributing factor. But nevertheless, you can consider this because that is also unknown. The second point, P of Z is a posterior, which is also untrackable, which is this is what we approximate with the Q distribution. And this is the main reason, second point is the main reason why we go to evidence lower bound instead of maximizing likelihood. So our correct option is both 1 and 2 are true. So I hope this was clear. If there are Any doubts, please let me know. Otherwise, I'll move to the next question. Now, given what I explained about VAEs, the two different loss functions, what do you think is the actual formulation of the final loss objective of VAE? We just discussed what are the two different loss functions. One is the reconstruction loss, one is the regularization loss. But how do we actually incorporate it, these two loss functions? So let me quickly pause for a few seconds, try to read the options clearly and take a guess in the chat. Yes, as all pointed out in the chat, the first one is the option one is the correct formulation. So we maximize the reconstruction loss and we subtract it with the regularization KL divergence loss. So this is a very standard loss function. So it comes from the same formulation when you start. If you look at the derivation, right, of this maximum likelihood, when you start deriving it using the elbow loss, you will end up with these two terms. So that entire recording has the clear derivations, but all you have to understand from VA is this is the final loss function. So if you don't remember the entire proof of how we are going from this loss function then to this, it's important that you at least remember the final loss formulation. Okay. Now let's little bit ponder upon the loss function itself. So this is the final loss function we just discussed. Okay, but there is still problem with this loss function, which is solved in the elbow loss. Okay, what is the problems that is there in this loss function that leads us to using the elbow loss tricks basically? So these are the four options. Please try to look at each option very carefully and answer in the chat. Uh, Let me discuss the correct answer. So let's see what are the terms involved firstly. Okay, there are two important terms. One is the P of Z, which is the latent distribution. Second is Q phi Z given of X. This is the approximation to that actual latent distribution, which we don't know. So we are approximating that with Q of 5. You can maybe, this is actually the encoder, in fact. Let's just call it encoder. Then we have P theta X given. This is nothing but the decoder, which is nothing but the reconstruction loss. So if you look back to the block diagram which we had, exactly these, right? P X given Z, this is the decoder, which will calculate the reconstruction loss. Q is nothing but the encoder aspect, and Q5 basically, decoder has theta, encoder you can call the parameters as phi or phi. And since Q phi is should be as close as possible to a latent actual distribution, which is P of Z, which is a standard normal distribution. So that is the KL divergence between Q phi and P. So that is what we have over here. Q phi is the encoder, P is the actual latent distribution, decoder is this P theta. Now, first option says optimizing the theta using gradient descent works well. Yes, sure, because you have what is the decoder? If you just focus on the decoder aspect is it's a neural network which has parameters theta. That is nothing but think of it like a simple multi-layer perceptron, right? So each weight is nothing but a theta parameter, and this will generate an output. And we calculate that loss p theta x of I given z, the log of that loss, log of this probability basically. So if I want to calculate the back propagation, I can just differentiate. Let's call this loss L. I can just do dl by d theta, and we can actually do the back propagation well because there's every part in this forward computation is differentiable. So the backward computation will also work. So theta can be optimized using gradient descent. First option is correct. Now let's look at the second point, phi part. What happens in phi is slightly problematic. So phi is nothing but the encoder aspect. But in between, we are having two values, mu and sigma. And then we are getting a z. Now, what did I say? Where is the z coming from? Let me write it down. Z is sampled from a normal distribution mu and sigma. This step is not differentiable because we don't know where is that random sample coming from. If we don't know that, how can we differentiate? So why do we need differentiation? Because we have to back propagate the gradients, right? We have to go back towards the phi parameters. That's how we optimize you update the gradients and parameters. So you update the parameters using these gradients in the back propagation. But if the step, the z step coming from normal distribution, that itself is not differentiable. There is no way you can go to these parameters. How do we? So this is the problem that phi can't be directly optimized using the gradient distribution because it involves an expectation across these underlying distribution. That is nothing but taking these random samples, which we don't know, which we can't differentiate. That is why option 2 is also correct because phi can't be directly optimized. It's a bit of a problem. To avoid that, the authors proposed reparameterization trick, which is a very simple trick. Let me write it down on the side. So they said instead of doing z sample from mu sigma, don't do this. Instead, z is nothing but mu plus sigma multiplied by epsilon. This epsilon is now sampled from a standard distribution. This is still equivalent to the above one. It's just that now we have very cleverly brought in the randomness only at the epsilon part, and we don't want to optimize this epsilon. That's not something what we want. We want to optimize mu and sigma. Now those are still differentiable. Epsilon, which is the randomness part, that is not differentiable. That's fine because we don't want to optimize that anyways. What we want to optimize mu and sigma, and now that is differentiable. So now the entire pipeline is differentiable. This is the reparameterization trick, which is which was very helpful in that entire optimization process. So option 3 is also true, and hence all of the options are correct. Let me pause for a quick second. Any doubts in this problem? Very important step, reparameterization. That is the reason why VAs work. Okay. Encoder doesn't depend on Z. Encoder predicts Z. What is the encoder equation? Encoder equation is encoder equation is it. What is the output of encoder? Z given Xi. So it is predicting the probability of Z for a given input. So it is not depending on Z. It is encoder output is the Z value. So I hope that difference is clear. Please let me know if that is not clear. I'll move ahead for now. Now coming to the next question, this is based on GANs or generative adversarial networks. That is a full form. So let try to first answer this question. I hope you all watched the recorded lecture. So based on that, try to answer this question. Which of the following statements are true regarding GANs? And then we can actually discuss how the GANs work and which of the options are true or wrong. Yeah, the correct option is 1, 2, and 3. Now let's try to understand uh, what is GANs and then look at the options. So GAN architecture again is very simple architecture. So VAEs had that encoder decoder architecture where we're trying to project it into an intermediate representation and try to reconstruct. GANs kind of took another path. GAN said, okay, let's have two networks. One is a generative network, one is a discriminative network. So generative network tries to create fake images. Discriminative networks try to identify what is the difference between a real image and it'll try to figure out given real what given an image whether it's a real image or a fake image. Very simple idea. So it's like there are two players in a game. One is the generative player which tries to create fake images. Another is the discriminator player. Think of it like this is like a generative to be like a thief. Think of this particular like a thief because it's trying to fake something. Think of the discriminator to be like the police. The job of police is to catch what are all the things that have been faked or what are all the things that are wrong. So generator tries to what is the goal or objective is it'll try to fool the discriminator by generating fake images which are as close as possible to the real images. Whereas discriminator is optimized with the objective that it has to try to identify the fake images from the real images. So this is the main idea behind adversarial networks. So the name adversarial comes because there's an two players who are kind of competing with each other. So that is the adversary part over here. So GANs are inspired from a very popular concept of game theory. So people who are interested can definitely look into connections between game theory and GANs. So game theory also talks about it's a field of science where basically it's a popularly used in economics and everything. It's basically how given two players, how can they work with each other in the best way possible so that the outcome is the satisfactory outcome for all of the players. That's what game theory says. Like given two people playing against competing with each other, what is the best plan of action they can take such that the outcome is beneficial for everyone? That's the most popular way of understanding game theory. There are different interpretations to it. Now, similar idea over here is you have two players posing with each other, and what are the inputs to each of these networks? Let's see. Generative networks, because it has to create a fake image. So it can create a fake image from random noise. So this low dimension latent space is nothing but think of it nothing to be like a Gaussian noise. So it is coming from a standard Gaussian distribution. It is just it sample this noise. From this noise, it generates a entire image of three channels, like something like 64 cross 64 comma 3. It generates an image. Now you already have real world images. Let's say that image is also 64 comma 64 comma 3. The discriminator will take input one image at a time. It could be a real image or a fake image, and the discriminator objective is based on whatever is the input. It's a binary classification task. It will predict whether it's a real image or a fake image. That's it. So very simple uh, uh, algorithm to understand. There's no complications to it. Let me pause for a quick second. Is the idea, the goal behind GANs clear? What each network is trying to do? What is the adversary part over here and everything? Okay. So if this is clear, then the few things that we have to take care while optimizing. The first important thing is the mode collapse problem. So what typically happens in mode collapses? Now let's say when the generator algorithm it is trying to create it starts off with random images, right? Because I don't know what can it. Obviously, when it starts off with random images, the discriminator can easily identify, okay, this is a fake image. Then it'll the generator will get a feedback, okay, discriminator was able to identify. It'll try to create more sophisticated images. So it's an iterative process, and in that iteration, it can maybe find out that there is one particular type of image that the discriminator can never identify that it is a fake image. It could be probably images of a dog class for some reason. We don't know why, but for some reason, images generated by this generative network of this dog class can never be identified by the discriminator as a fake image. So then the generator will take this as an advantage and it will exploit by generating only dog images. It will not diversify. It won't generate images from other classes. It will only generate dog images. So then we will see, okay, generator loss is very low because it is able to generate with high fidelity images that discriminator cannot catch. But that is not true. What it did is a more hack kind of an approach where it identified a particular loophole that okay, dog classes is something the discriminator is not able to pick as a fake class. I will only predict dog images so that I will be happy with my loss being less. So that is the mode collapse problem. So mode is nothing but different classes. So it will typically identify what is that one particular mode at which the discriminator fails, and it will just keep on generating output for that particular mode. Mode is nothing but the peak. Okay, let me go back. So if you have a probability density function, so typically you have a peak like this, right? You can think of this peak to be the mode, the highest frequency values that appear. So typically you have multi-mode distributions, multimodal distributions, like multiple modes will be there. So in generator network will try to identify which is that one mode which probably it will do better by fooling the discriminator, and it'll just keep on exploiting. So then the diversity won't be happen. All of them collapse into one mode. That is the mode collapse problem. So very fundamental issue, and there are several techniques to avoid this. In the way they reformulate the objective function and everything. But that is a fundamental issue in GANs. Okay. Now let's go and look at the options. So first option says difficulty in training due to the zero sum objective. What is the zero sum objective? Zero sum objective, like I said, it both of the players try to pose each other and try to get the lowest objective. So if you think of it in terms of min max formulation, the generator tries to minimize its parameters. Let's call it G. The discriminant tries to, sorry, so generator will try to generate images, like maximize whatever the parameter such that its output looks as close as possible. Discriminator will try to minimize its loss, where it will try to identify between the fake and the real images, and there will usually be like a max min approach, and we want to try an equilibrium between these two players. What is that equilibrium? Where both of them are in a optimal position. That is nothing but the zero sum objective, where both of them are benefiting and their overall an equilibrium is established. So that is what this particular thing says, that this is a zero sum objective problem, and typically zero sum objective is hard to solve. You will need a lot of epochs of training. There's a lot of stochasticity during the training also. You'll need a lot of samples also, and etc. So first option is true. Second, mode collapse, which I just explained how all of it will try to identify the most common node with which it can fool the discriminator. It will just try to predict that. Third is evaluation of these generated images is actually not very straightforward. It's not just for this particular GANs. In general, evaluation of generated images, even in today's time, even with diffusion models and all, which you'll see in later classes, while there are techniques, while there are evaluation metrics, it is still a very subjective thing. It's not very clear how the evaluation of these images can happen. So that is why three options is also true. So correct answers are 1, 2, and 3. I hope this was clear. Let me move ahead. This is the actual formulation. So, oh, sorry, my bad. It was minimum of G and maximum of D. I interchanged the min max previously. So the G is the min player, the max is the D player. So this is the actual formulation of the loss function. Now consider, suppose the true generator distribution and the data distribution is given. True generator distribution is nothing but PG. The data distribution is nothing but PD. Let's say if these both are given, then what is the optimal discriminator? So you have to basically identify how do you find optimal. You differentiate this problem. That's how you find the optimality of differentiate this function, right? So let's say the truth generated distribution is given to us. So after we differentiate, if you apply the truth generated distribution, what will be the optimal discriminator value? So it's a slightly involved problem. So this is how it will look like if you expand. So if you differentiate this particular term, this is what you'll get. PD divided by PD plus PG. So I've skipped this because it takes a little bit of pen and paper to solve. Maybe in the interest of time, you can look into it at your own time and get back to me. But this is the process. So this is how the equation formulation is. You expand it by expanding the expectation uh, formula, and then we differentiate that to identify the optimal value. And this is what you get: PD divided by PD plus PG. Okay, let's go to the last question. What is the typical metrics that is used to evaluate the quality of a generative model? Out of these four, what are the typical evaluation metrics that can be used? So I hope you were able to watch the recorded lectures. This has been discussed over there. Try to take a guess. Maybe you can think where you're going wrong. One small uh, edit in the question. So this is not IS score. This is Frechet ID score, or it's called as FID score. So it's a multi-correct answer. Two options are correct. Yes, first one is correct. IS score, which is inception score. There's another correct answer also. Yeah. So the correct options are one and two, as mentioned in the chat. So let's look at these scores itself. I'll give you a high-level overview. The first one is the inception score. So inception network, I hope you are aware of it. It's a very popular CNN network. Just like how ResNet is one popular network which uses residual connections, Inception network was proposed by Google, I believe, and it had a lot of benefits. Like it had multiple different kernels. That each Inception block had 4 5 different kernels. All the outputs were pooled together or stacked together, or some concept like that. But what Inception Score says is it basically tries, it sends the real, any generated image, right? It sends that as an input to the Inception network. It gets the output, and the output is evaluated as the KL divergence. Basically, it's like a expectation of the KL divergence between the predicted distribution probability of y given x, KL divergence of that distribution, and the distribution of y itself. So two things happen with this loss. Number one, it will try to predict it try to understand whether the generated image belongs to any one of the classes. So it classifies, checks whether it can be classified or not. Okay. Check whether the generated image can be easily classified or not with high accuracy, with high confidence. Check for classification. And the second one checks py kinds of checks like the it tries to increase the entropy. So it'll check for what is the diversity of different classes. Like each generated images, right? Is it belonging to different classes or not. So it'll check for diversity of classes. So this is what these two things are checked for. So you're not comparing it against any real world image. It's just that we're comparing the quality of a generative model itself by generating a bunch of images and trying to check whether the generated images can be easily classified into one of the given classes with with high confidence. And the second is, can all the classes be generated from this particular model and not just few classes? That is the diversity. Next is so higher the inception score, high inception score means high better generative model. Then comes FID score, which is nothing but Fletcher inception distance score. So here what it does is it again uses inception network, but it takes two inputs. It takes the real image as an input, takes a generated image as an input, and then the output. I think typically the output of the third layer, third block of the inception or something, it's taken, and this output vector is then you take a lot of real images, like a lot of generated images, you then output all of these vectors from the third layer, and then you model using Gaussian distributions. When you find out the distance between the two Gaussian distributions, that is nothing but distance between nr minus ng. So distance between the real Gaussian distribution and the generated Gaussian distribution. So the smaller the distance, the more the generated images look like real world images. So FID lower implies better. Inception score higher implies better. FID lower implies better because the lower the FID score, it means the distribution gap between the real images and the generated images is smaller. It means the generated images is able to generate more realistic images. So that is what the idea of FID score is. So, are there any doubts in any of the problems or any other questions related to these concepts? If not, we can move to the code aspects of today's session. Let's go to the code aspect. So today in the code walkthrough, we will build a DC GAN architecture. So GAN, we know it's a generative adversarial network. DC stands for the Deep Convolution Generative Adversarial Network. It is nothing but uh, instead of using MLP layers for generator and discriminated, we will use convolution layers. It's just that. So it's DC stands for Deep Convolution Generative Adversarial Networks. So there's a lot of description. You can please read it at your own in your own time. What we just describe what are GANs and how do we typically have GANs mechanism. There's a discriminator network. There's an adversary generator network, and how these two compete with each other. All of this what I just described. So this was the loss function which you just saw also. Min-max formulation where you want to minimize the G parameters, maximize the discriminator parameters. One important point is here. So in this particular example, we use these dimensions. DC can also uses the same dimensions. The input image is 3 cross 64 cross 64. So typically the generated image will also be generated with the same dimension. The real world images are also using the same dimension. And the data set which we use is a very popular data set called celebs face data, real celebrities facial data. So it's called celeb face data set. And Z is nothing but the latent space vector where I said, right, initially you need some noise to go into as an input. So if you remember, this is the Z vector. This is Z vector. The 64, 64, 3, 64, 64, 3 is the input dimensions. And we have generator, which is all CNN layers, and the discriminator, which is again all CNN layers. So the only catch is in generator, What? Okay, let me ask you a question. What type of convolution layers should be there in the generator? What type of convolution layers should be there in the discriminator? What I mean by what type means, is it like dilated convolution, transpose convolution, or any other type of convolution? So what do you think should be there in the generator network, and what should type of convolution layer should be there in the discriminator network? Think carefully what we're trying to do. We are basically going from lower dimensional space to higher dimensional for generator. For distributor, we're going from higher dimensional space to lower. So based on that, try to take a guess. Okay, so let me explain that. So generator network will typically use transpose convolution. So if you remember when we're talking about CNN networks, transpose convolutions is a special type of convolutions which was also used in segmentation, in the decoder block of segmentation, where you go from smaller feature sizes and you project them into bigger feature sizes, like going from this low dimension latent space to 64, 64, 3, right? How do we do that with convolutions? You do using the transpose convolution modules. Discriminator will use the standard convolution because in we want to reduce the feature space from 64, 64, 3 to simple binary classification, which is nothing but 2 as an output binary vectors with dimension 2. So here we use the standard convolution network. So those are the main points which are needed for you to understand what is need how do we build the DC. Now let's go into actually building one. So as usual, always important to import all your libraries at one particular place. We have a bunch of different libraries, PyTorch. Inside PyTorch also CUDA NN, which is used for communicating with the GPU. Then Optim, which is used for the optimizer part. Then data and data sets, transforms for pre-processing. Then NumPy for general multiple array-based computations and linear algebraic computations. Matplotlib for visualization. We also set the random seed, highly important. At this point, everyone must be aware of it. Random seeds are very important for reproducibility to ensure, especially with adversarial networks, right? Even after keeping all your random seeds uh, fixed, right, there is a chance that there can still be some stochasticity in the output accuracy or output performance metric. So, very important that you definitely have to try to keep the random seed fixed. Now, these are some of the input uh, variables which we will define. First one is the data root path, that is the standard path of the data set. Workers, very important because data loaders functionality is create mini batches of the data set, and all these mini batches are created and they're not actually stored actively. So, as far as my understanding goes, they are all present in the secondary memory. Data loader understands the logic of how to create a mini batch, and with the help of workers, whenever you're doing your model update, whenever you're doing your training, it it takes one or few of the workers, gets the mini batch from the secondary memory to the RAM, does the model forward pass, loss calculation backward pass, then updates the gradient weights and everything. Then once that is done, it will send that mini batch again back to the secondary memory with the help of these workers, and it brings the next mini batch to the RAM. So that is how data loader functions. So this workers variable is very important for you to um, reduce the latency between this travel of mini batches from secondary memory to the RAM. The third is the batch size, which is very straightforward. It's nothing but number of samples or number of samples of the data set present in one batch. That is nothing but the batch size. Image size is the input image height and width. In this case, it is 64 cross 64. You can always create different, you can take different images of different sizes and do the same. Number of channels of the input image, since it's a color image, it's 3. Latent vector size, typically, I think in this case it is 248. Yeah, no, 100. 100 is the latent vector size. Then we have NGF. This is nothing but the depth
of the feature maps which generator creates, and NGF is that. NDF is the number of feature maps that is propagated through the discriminator. So in this particular case, both of them are 64, feature maps in generator and discriminator. Number of epochs is the number of training epochs that we wanted on the model. And learning rate, beta is used, this is a hyperparameter for the Adam optimizer. So it is typically set according to the paper as 0.5. And number of GPUs, always used GPUs. If your output is saying 0, right, typically means it's in the CPU mode. If anything other than that, it means it's usually in the GPU mode. This is one different parameter variables what we just discussed. We create all of them. So this is the data set. You can download it in the PyTorch. You can download it using this Google Drive link, and this is how typically the data set looks like. The data directory of the data set. You first download the data set, and once you download the data set, you create this data set structure in PyTorch using the data which you downloaded. So you mentioned the data path and everything, and then you make sure this. So this is an inbuilt image folder, is an inbuilt PyTorch functionality, which basically creates a data set from the image folder, whatever you have in your Google Drive or local machine or whatever. So it will open each image and does these transformations on these image, like resize the image, crop the center part, convert into tensor and normalize. It does all of that and creates a dataset structure of PyTorch. So that is what this particular dset.image folder does. It also has some functionalities like how many items, what is the length of the data set, how do you open each image in that get item function. All of these you can look into the documentation, but on the high level overview, this is what it does. It takes the path to your dataset where it is downloaded, all the images, and then whenever call this, it basically opens all the images, transforms them, that is pre-process each image according to the ones which you specify, and all of them are stored into a dataset structure. Then is we create the data loader. Like I said, data loader is main job is to create mini batches from in your entire data set. So that's what each batch size will tell you how many batch samples in each mini batch, and like that you divide it by across the total data set. And shuffle equal to true, very important during the training, because it will make sure that the mini batch consists as many diverse samples as possible and not samples from one particular class. So always ensure shuffle is equals to true. Number of workers, which I already defined. Then we check the device, whether it's a GPU or CPU. That is, you can do torch.device. And how do we check? We check using this torch.cura.is available. This basically say if a GPU is available or not. If it's available, we specify CUDA 0. If it's not, it will be a CPU. So always print the device and check what you have. So now let's plot some examples. This is how it looks. So we just pick one mini batch from the dataset which we have, and then we plot it using the matplotlib. So these are the image samples present in one mini batch of the dataset. You can see a lot of famous people like Bill Gates is there, a lot of movie and actors, and also singers and football players and everyone. So this is a dataset of all these celebrities basically. Now let's go to the implementation. Before that, the DCGAN paper initializes each of the weights in the following manner. It uses a normal distribution with mean 0 and standard deviation 0.02. So that is what they found to be like a hyperparameter which worked the best for them. So we also try to, since we're replicating the paper, we also create a function weight in it, which will basically create the initialize all the weights using the normal distributions with the same 0.0 mean and 0.002 as the standard deviation. Now, this is the generator architecture. We start off with 100 dimensional vector. We reshape it and project it into higher dimensions, 4 cross 4 cross 1024. Then we do another convolution where it goes from 8 cross 8 cross 512. Another convolution 16 cross 16 cross 256. Another transpose convolution 32 32 128. Finally, we come to the original image input resolution, which is 64 64 3. Okay, these are all transpose convolutions. So now let's look at the architecture itself. As usual, till now, whatever we discussed, if it's a neural network class, always inherit the indent dot module parent class. Very important, because this will tell PyTorch that this is a neural network class, and then it will attach all the default functionalities like backward pass, forward pass, function. All of these things will be attached to it. Otherwise, it won't make sense. There will be no backward function by default attached to this particular neural network, and all the other functionalities. Typically, we only modify two functions in this class, which is the init and the forward function. Remaining all, unless you are coming up with newer ways to do model learning, you can modify, customize it. Otherwise, it is fine. Init function, basically here we define the different layers we want to use, the different variables you have. All of these things are defined in init. In forward function, we typically mention what is the data flow, like from the input to the first layer to the second layer, how the data is flowing. And as usual, there are two ways to create a neural network. One is using this nn.sequential, this which you're seeing today. Others was with what we did till now, where you define each layer separately. In the forward function, you manually take that data and send it to each layer, and the output of that layer will go as an input to the other layer. That all manually you write it in the forward function. In sequential, in the init, you define all the entire architecture, all the layers. Like here you see, first is the transpose convolution layer one, then batch norm, then ReLU, then another convolution batch norm ReLU. All of these layers you define, and in the forward, you just call this sequential layer and you send the input. Automatically, the data will flow in the same manner as you mentioned in this sequential class. So you don't have to manually send the input from one layer to another layer. So that is the difference between sequential and end of sequential way of creating, and the other is more manual way of creating. So there are pros and cons to both. Depends on how much customization do you want in your model. In this case, since we don't want much, we just use sequential. So here the same. We start off from 100 dimensions. We project it into 64 into 8, and 4 is the number of kernels we use. 1 is the padding. Sorry, 1 is the stride. 0 is the padding, and bias is false. Batch normalization and ReLU is standard again. Next, we go from NGF2, which is 64 into 8 to 64 into 4. Similarly, we keep on doing it until we reach the final size 64 comma 64 3 comma 64 comma 64. That is the final output of the generator network. And in the forward function, you just send the input and you get the output. Now, this is how you create an instance of the class generator netg. You then send it to the device. You do this nn.data parallel netg. It will handle multi GPU if you want. And then we apply the weights init weight function where we initialize all the weights. That dot apply is another default functionality which is present in neural network class in PyTorch. So if you didn't do that nn dot module, that if you don't inherit this nn dot module, right, this apply function will not work for you. So it's important for these aspects that you need to inherit the nn dot module. So dot apply will initialize the init weight function, and if you print the net g, this is what you see. Initially it was 100, then you have 512 channels, then 256, then 128, 64, and finally 3 channels. And corresponding to the features also keep on reshaping themselves, and finally it is 64 cross 64 cross 3. Okay. Any doubts till now in the generator architecture, any other component in the coding aspect? Okay. So if there are no doubts, then let me go ahead. Next is the discriminator. The idea of discriminator is very standard. Just like how you have traditional CNN networks, right? You take an input, you keep on learning the features using CNN networks, and then you predict a binary classification, whether it's a real image or a fake image. So architecture remains very standard. Again, we use nn.module inheritance, and here we sequential. We start off with the first con2d. Number of channels is 3. Output channels is 64. Number of kernels size is 4. Number of kernels is yeah sorry size is 4. Stride is 2, and the padding is 1, and the bias is false. And you keep on having a bunch of different contour layers. After contour, you do activation. In this case, we use leaky Raylo, and we keep on doing this until the output is 64 comma 1. So one output you get, not 64. Sorry, you just get output as one particular value, and this one value will basically tell you if that value it's a logit value, right? You convert it into probability, and if that value's probability is closer to 1, it means it's a real image. If that output value is closer to 0, it means it's a fake image. So that's why you use sigmoid activation function to process the logit into a 0 1 probability. Like it squishes the value of the logit between 0 to 1, so that if it's closer to 1, it's real image. If it's closer to 0, it is a fake image. Since it's NN sequential, we just in the forward function just mention the input data, and it will pass through the entire neural network layer after layer. Same way, if you want to create an instance of discriminator, send it to parallelize it by sending it into nn.data parallel, apply the weight initialization, and print. This is what we see. Now let's come to the loss function. Yes, batch normalization is a design choice. So the advantage of batch normalization, there are multiple advantages. It avoids overfitting. It also speeds up the training process. So because of these advantages, batch normalization is typically used in many deep learning architectures, along with dropout sometimes, other regularization techniques like L2 norm, L1 norm, all of those two. L2 regularization, L1 regularization, all of those are also used. Okay. Coming to the loss function, since discriminator has just a binary classification, we use binary cross entropy loss. This is a simple binary cross entropy loss where if the output belongs to the ground truth class 1, the first term will get activated. If the ground truth belongs to class 0, then the second term will get activated. That's it. Very simple loss functions, just like a mini version of your actual cross entropy loss. In our case, if it's a if the ground truth, it's a fake image, right? It's a fake image means ground truth y will be 0. It means the second term will get activated. Similarly, in if the ground truth is 1, it means that fake image that is coming it as true, and the first term will get activated. Now what is the x in our case? This first term will be log of d of x. It means we want to, whatever is the output of d of x, right? We want to increase that value closer to 1. The next option is log of 1 minus d of g of x. It means that x is coming from generator. That is why g of z. And this we want to make it 1 minus d, right? So we want to make this value as less as possible. It means as close to 0 as possible. So that is what this binary cross entropy losses does. So we want to confuse this discriminator by not doing this particular differentiation factor easily. This is the binary cross entropy loss, and these are the two optimizers, one for discriminator, one for generator. Both of them are Adam optimizers. And we also have ground truth labels. Real label will get 1, fake label will get 0. This is some fixed noise which we will sample, latent vectors which will sample to visualize the progression of the generator. Okay. So this is basically how the training happens. It happens in multiple parts. The first part, we train the discriminator. We maximize this particular loss function. And since we have separate mini batches, we will calculate this in two steps. We first construct a batch of real samples. We send it to the discriminator D. We calculate the log of this value. Then we calculate the backward pass of that. Similarly, for fake samples, we create a batch of fake samples. We send it to the discriminator. We calculate this loss, log loss, and then we do another backward pass. With these two things, we finish the discriminator training. Then the training of the generator comes in, where we just minimize this log function, this loss function, log of 1 minus d of c, in order to basically generate better fake images. If you want to visualize, these are the different losses we can visualize: discriminator loss, generator loss, the our average output, and the average discriminator output for all fake batch samples. Now let's look at the code itself. So these first are nothing but just keeping track of what are the different losses. So that is the list of these. Now the training happens in two for loops. One is the epoch for loop, and the other is the mini batch for loop, the standard with all neural networks. That's how mini batch gradient descent happens. So we first zero out the gradient as usual, always important, especially in these. It's important in every network, especially in these also, where you make sure that no residual gradients from previous updates linger around when this particular new step starts. So we zero out those gradients. We then mini batch the real data and we send it to the device. And then, since it's real, we create a variable label which has all one value. Real label is one, right? I'll create for that mini batch samples all one values as the ground truth label. We send this as a input to the network, discriminator network, get the output, calculate the cross binary cross entropy, and that is we do the backward pass. That is calculate all the gradients. We don't update the model yet, we just calculate all the gradients. Then we take the random noise, we send it to G, we get the fake images that the generator outputs. We then create the label for this fake, which is all zero. We send it to the discriminator, get the output. We calculate the fake error, and then we do another backward because calculate the gradients of these fake error loss. And then the total error on the discriminator is real error plus the fake error, and then we update the model using the both the gradients, the fake gradients and the real gradients. Now similarly we update the G network also, where we take that labels output values from the G values, and then we calculate the gradients of that using error G dot backwards, and then we update this. Very simple. In these same three steps, we what we just discussed in the theory, we just did it in the we this other parts is nothing but just to keep track of what the different losses, how they propagate throughout the training process. That is nothing but just checking after every 50 iterations, store the losses, after every few epochs, store the losses and all. So this is how the model trains. You can see the discriminator loss, the generator loss, the mean discriminator output for real images, mean discriminator output for fake images, all of these values. So we finish for 5 epochs of training, and this is how it looks if we plot. So the generator usually goes up and down, up and down, up and down because it's a equilibrium state, right? Sometimes it's good, sometimes it's bad. Similarly, the discriminator also keeps on wobbling between up and down. And these are some of the images that have been introduced. So just by simple 5 epochs, the model is able to actually decently generate, like, while it might not look like an exact human face, we can still see most of the aspects have been covered, like, okay, where the eyes should be placed, where the nose, mouth, everything. Remember, the this fake image is coming from a random Gaussian distribution. Okay, there is no way any information has been given to that noise. It's just a random noise. From that random noise, the model is able to actually generate these nice celebrity faces. While of course there are some issues like this particular hair and all, like it's little bit hazy, but still very good compared to given that it's just trained for 5 epochs. Okay. So this is what I wanted to discuss. You can then check out a bunch of different things where you want to generate music and all of these things using GANs. You can definitely go to those particular tutorials and figure those things out also. So generative algorithms, it's not just typically used for images, uh, image generation. It can be used for anything. It can be used for music generation. It can be used for text generation. So any of these generative algorithms can be used. Okay. Okay. That's what I wanted to discuss. Any doubts or anything that you want me to discuss once again for this particular live session? If there is nothing, then we can end today's session. Okay. If there are no further questions, I'll just stay on the call for 5 more minutes. Okay. I think there's a question. We have an encoder decoder, so why we need this? We don't have encoder decoder in GANs. Wait, let me go back to the architecture. This is the arc. There's no encoder decoder in GANs. Encoder decoder was there in VAs. So you can think of, if you want this generator to be like a decoder, because it is going from low dimensions to high dimension, and discriminator to be like an encoder, but we don't call that. The purpose is also very different. Encoder decoder was in VAs. GANs just have generator and discriminator. Yeah, yeah. You might probably be confused because of the way these blocks are drawn, but it has nothing to do with encoding decoding. It's very different purpose in GANs. Yes, generators always produce fake images. That is the concept. That is the only objective of generators. Always generate fake images, realistic fake images, as close as possible to realistic images. We are using it because we want to generate. So, for example, uh, if you have a generator that can generate fake images which are as close as possible to the real images, then we can condition this generator to generate images which were not there in our training data. For example, now we had all the faces data set, right? And all the faces, let's say, of all Western US celebrity faces. Okay. Now, ideally, I want to generate an image of Indian actors, but that was never there in the training data set. But the generator is able to generate faces very good. So by conditioning, like few other techniques, by conditioning the generator, I can now generate Indian celebrity data as a very realistic image. So that is why these generators are used. So the training process it generates the fake images to learn how to even generate images, face images and all. But once you finish training, you use these generator to actually generate images which was never there in the training part. You generate newer images, just like how, think of it, how you nowadays people generate a lot of AI based images, right, using GPT and all. Uh, They don't use something like GANs, but you can think of where is this coming? They're generating some images which are not existing previously. So think of it like using generator and conditioning that generator on certain aspects to generate these new images which were previously not there in the training data. I hope that is clear, the purpose of the generator. No, the data on websites. So, okay, now the question is, you are assuming that there is a data for every type of image that is possible. Okay, for example, like say there are faces of images. Okay, that is image faces may be limited. Let's say all the hype around you can create whatever image. Like imagine you want to create yourself back in the what do you say uh, Indus Valley civilization era. There is no image like that available on the internet, right? How do you create such images where nothing like that exists on the internet? That is where we need these generative algorithms. So the fake image process is for the model to understand what should the element of images should even contain when it is trying to generate some type of images, right? It should understand what is it that makes an image a realistic image. That is what the training learns. And when you ask this generator network in the inference time, generate an image of myself in Indus Valley civilization, since it knows what is the realistic image, it can create yours, keeping you into an Indus Valley civilization and create that image in a very realistic manner. So that is why you need to go through this training process. So I hope that's clear. Yeah. So ideally, it should not, right? If generated images are trained from training data, then the architecture itself will firstly not look like this because you're going from low dimension. Let's say somehow instead of generator network, you're using these auto encoders. Okay, you're then creating, reconstructing the original input with this generated output with this autoencoder, then ideally discriminator should not differentiate as long as your autoencoder is doing its job correctly. But that won't help in any way, right? What is the point of doing that? Because generated images are still being trained on real world. That will always limit that. That autoencoder is a limiting factor, right? It can't generate out of the box images. It will only generate images which it has seen previously. Yeah, all of the algorithms that I talked about, like GPT, Gemini, all of these image generation models, diffusion models, all of them do these things right now. Diffusion models is a more superior version, which probably we'll start covering in the next session, compared to GANs. So GANs were popular probably 8 years down the lane previously. Then diffusion models came and it took over GANs. But still, some people still use GANs nowadays, so it's relevant to learn these algorithms. If there are no further questions, we can stop this call. Yeah. Thank you all for joining and for your questions. Uh, I'll see you next week.